Hi there, this video is going to explain the action of a bipolar transistor circuit. It's an amplifier circuit. It's configured in common emitter mode. So what we're going to do is we're going to change the values of the output transistors, which is R4 and R3 that define the voltage gain. We're going to use these particular values. The theory says minus R4 over R3, and we're going to see in an actual circuit what the gain actually is. And we're also going to do a half voltage test so that we can see what the output impedance of this circuit is, so that we know what kind of loads we're capable of driving at full open circuit voltage. At the moment we've got 6K8, 1K2. We expect the gain to be 5.67. Let's have a look on the screen. The yellow one's 1.0 volts peak to peak. We've got 1 kilohertz, and what we've got there coming out jumps a little bit. We've got 5.56 minus 5.56 actual gain, which matches very closely to the R4 divided by R3. What we're now going to do, that's the open circuit voltage. We're now going to connect a load into it so that we get half the voltage out, so that we can determine the internal resistance of this circuit. So connect black box in there, and what we're looking for is half of 5.56. so what we're looking for is, let's say, 2.75. so at the moment we've got 2.2, we want 2.75, there's 2.76, and what we've got on the black box, if we read it off, we've got 6K5. So I've got 6K5 load on this circuit here to get half the voltage out, so that we know the internal resistance of this common emitter amplifier is 6K5 with these particular resistor sets. What I'm now going to do is change this one to 4K7, change that to 4K7, change the other one to 2K2, and the gain from theory now should be 2.14. and what we're going to look on the screen, we need to disconnect the black box just now. The load resistor, the open circuit voltage should be 2.14. Jumps about a little bit, but yeah, 2.16 minus 2.16 is the gain on the actual circuit, which is pretty close to the theory. What I'm now going to do is put the load in, and what I'm looking for is 1.08, so we'll say 1.1 volts. So I'll adjust that to get 1.1 volt coming out, and adjust it down, that's too far, that's 1 volt there, 1.1 volts coming out, 1.1 we're looking for, it is jumping up there. Yeah, we'll use that. So what we've got there is 3K9. We've got 3K9 for that one. If we go to 4K9, yeah, we're looking for 1.1 volts. We're not quite there, that's gone too far. So 1.1, 1.1, 1.1. Yeah, that's better there. So we've got 4.4. Score that one out. We've got 4K4 for that one. That's better measurement. And what we're now going to do is disconnect the load box. We're going to do 2K7, so we change that to 2K7, and we've got 1K2, 1K2, so the gain from theory should be 2.25. What we've got here is the gain coming out is, have we got that, 2K7, yep, and 1K2, 2K7, 1K2, 2.25, it's coming out to be a little bit higher, 2.4 there. If we just have a look at channel 1, is that still 1 volt? It's a tiny bit up there, 1.06. We'll go back to there, we've got the gain is, we'll call it 2.36. And that's open circuit, so let's put the load box in. So what we're looking for is half of 2.36. So we're looking for 1.15. We'll look at 1.15 coming out. So we turn that down, 1.15. There's 1.16, and we've got 2K4. We've got 2K4 coming out. So we're doing the half voltage test to determine the internal resistance of the common emitter amplifier, and what we can see from these values, apologies for that one, when R4 is 6K8, the internal resistance 6K5, 4K7 it's 4K4, 2K7 R4 is 2K4. So what we can see here is the internal resistance, the output impedance of this circuit, is determined by the value of R4. So that's been determined by experiment. What I'm now going to do is to determine the frequency response when we have the circuit in this mode. So what we want to see is we've got 1 kilohertz at the moment. We'll disconnect. We want the open circuit voltage again. Disconnect that load resistor. What we've got at the moment is 1K, and we've got 2.36 as the gain. If we up the frequency to 10K, do we still get the same peak voltage coming out? Yep, we still get the same peak voltage, and by the way, it's inverted because it's a common emitter amplifier. If we turn it up to 100K, do we still get the same voltage coming out? Yep, we absolutely get the same voltage coming out. You can see there, 2.36. If we go up to 1 meg, we can see that, we'll just double check that, we can see that the voltage has gone down. So the voltage is now reduced. So why would it be reduced at higher frequencies? It's reduced gain at higher frequencies because effectively it operates as a low pass filter. So at high frequencies, any capacitance, any parasitic capacitance between pins will tend to short out the pins and will tend to short out the circuit, so that the gain is now no longer 2.36, it's substantially reduced. So it does have a 3 dB cutoff, and that is due to parasitic capacitance between the pins. Effectively makes it a low pass filter. So we'll go back to our 1K again. We'll go back, sorry, that's 100 ohms. We'll go back to 1K again. What we want to do now is we want to change this circuit so that we change it into a digital NOT gate rather than a transistor amplifier. So we're going to do, you only need to do 2 things. So one of the things you do is the resistor on the emitter needs to be substantially lowered so that we get massive gain out of the circuit. And what we do there is we're going to change that to 10 ohms. We'll just readjust this again. So we've changed this value on the emitter, and we can see now that we're actually getting a digital signal out, and it is going between 0 and 15 volts. The way to alter that to get it to TTL levels, 5 volts, is to change the power supply rail, and what we now get out is a digital signal. It's bouncing, it's a discrete signal only going between 0 and 5 volts. So we get analog in, digital out. If we change that to a square wave, we've got square wave going in, which is that yellow one there, and we get a 0 to 5 volt signal coming out. So it's TTL levels, it's inverting, so it's a NOT gate. And we can turn the voltage down to very low levels and it still continues to work because we've got effective massive gain in the circuit, because the transistor has been switched fully off and it's also been switched fully into its saturation mode so that we get maximum voltage out. So when we have 0 volts going in, the transistor is switched off and it pulls the collector rail to 5 volts. When we switch the transistor into saturation mode, we have maximum current going through the collector and emitter, and it pulls the collector voltage down near to 0 volts, which is what we get here. So just 2 changes, 5 volt rail from 15, and R3, the emitter resistor, we change down to about 10 ohms. Even if we put it down to 0, yeah, it still works. So we need 10 ohms or below. If we have too much resistance on the emitter circuit, it starts to affect the 0 volt level. So we set 2 changes on the circuit, 15 to 5 volt rail, and change the emitter resistor down to about 10 ohms. We now change the circuit from analog to digital, it's discrete, and we get a 5 volt TTL output. It's a NOT gate, 0 in, 5 volts out. High signal going in, we get 0 volts going out. Thank you for watching.